We want to talk about 1.5, existence and uniqueness of solutions. So this time we want to focus on the initial value problem. Okay, which means we have an initial condition and we have a differential equation. For first order, we just put things in this way. Okay, and y0 equals y0. Okay. If you think about what we have done so far for initial value problems, basically we have the following things. We have some phenomena in the nature, and we know they satisfy a certain kind of physical law. Okay, and also we give people the initial condition, so where to start with. So technically what we know is, we know at first where you are, and then we know what your change will be, how the whole thing is going to change, described by the differential equation. So together, if I know where you are and I know how you will change next, I will be able to predict what's going to happen in the future. Equivalently, I will be able to backtrack what happened in history. Okay? So basically, this is all about predicting the future. Knowing what's going on right now, which is the initial condition, and knowing how things are going to change. Given by the ODE, you will be able to predict what's going to happen in the future. And if you take your time to be negative, you will be able to backtrack what's going to happen in history. Okay? So when you do that, of course, you want two very, very strong restrictions. The first one is existence. That is, can you even do it? Is the future predictable? Or if you have a differential equation, or actually any kind of equation, can you even find a solution? Is the solution solvable? Is the equation solvable? Does there exist a solution? Okay, so that's existence of solutions. The second thing, well, if there exists at least one solution, it is possible that you have multiple solutions. So if you start from here, following the same trend, sometimes you go into this, sometimes you go into this, sometimes you go into this. For that, you have very bad predictions because you don't know what's going to happen on which track because your future has multiple possibilities. Okay? So for that, what you want is actually you want the future to be uniquely predictable. That means there's no uncertainties. There's no guessing where it's going to be because you have multiple possible tracks. Okay? It's uniquely predictable. Only in that case you can actually start to use a computer to simulate it, because every time you have a computer, you use a numerical method, you will always only have one solution, right? Y1 depends on Y0, Y2 depends on Y1. So if you do numerical solution, you will always have one solution. But if the original problem has multiple solutions, you really don't know which one you're getting, and maybe you're getting neither one. Okay? So that's very important for solving differential equations combined with initial conditions. So now we want to give you the theorem that will guarantee, under some cases with a nice property requirements on the derivative or the right-hand side, you can actually have these two properties. Okay? So the first one is the existence of solution. If this is not satisfied, don't even bother to solve it. Okay? We call it a theorem. And we require, suppose the right-hand side, fty, is continuous. In a rectangle, given by ty, okay. T is between a range, and y is between a fixed range in the ty plane. Ty. And if t0, y0 is a point in this rectangle, then there exists a epsilon, such that, and f0 and a function ft. That solves y prime equals ft y and yt0 equals y0 in t0 minus epsilon less than t0 plus epsilon. Okay. It is a lot to write down, but if you think about it, you only require two things, okay, in order for this one to be solvable. Number one, you want this function to be nice. When we say nice, it should be continuous in terms of t and y. You don't have holes, you don't have jumps, you don't have vertical asymptotes. Okay? Second, what do you require? You require your initial condition will be inside a rectangle, okay, where the function is nicely defined. And then your solution only exists for finite time. So if you draw a picture, it's pretty easy to see. Let's say if there is a rectangle, and within this rectangle, your function is nicely defined for your derivative is nice. Okay. Then your initial condition is somehow in this, not here, but it's inside. What you can guarantee is your solution is going to exist. You will have a solution at least for finite time. If you go beyond that, maybe there's no more guarantee. Okay, simply because, we only know the functions are nice within this rectangle. So if you go beyond that, there's no guarantee you will still have a solution. But at least for finite time, it will happen. Okay? This epsilon can be big, which is what we want. We want the solution to exist from, negative 100 to positive 100. The longer, the better. The best is actually it exists for everything. So you will be able to all the way track the whole thing to negative infinity or positive infinity. But sometimes epsilon can be small. That means the property of your nice function can only guarantee that this might exist for, 1 minute. But the good news is you can always repeat the trick. So for example, if you see this, okay, and you check the derivative around it, you find, okay, the derivative is nice. Therefore, this one exists at least from here to here. Then you go to the edge of this one and start to check the derivative around here. If the derivative here is great, then you can guarantee you can extend this solution to here. Then you pick a point, you repeat the analysis. Okay, check the derivative around. If it's nice in this rectangle, you can even extend this one to here. So if the derivatives are nice in general, okay, for a very, very long period, actually you can extend your, existence of solutions all the way to a very, very wide interval. So in general, this is not too much trouble, as long as your derivatives is nice. All right? So with that in mind, we can see a very quick example. Y prime equals 1 over t. Y0 equals 4. Okay, this is the initial value problem. Let's put it in standard position. Okay, do you have a solution? Well, if you think about it, what I have is my fty is 1 over t. 1 over t is clearly not continuous at 1. Not at t equals 0. Okay, but sadly, your initial condition was given at y0. This one is at 0. Therefore, there's no rectangle such that my function is continuous. Meanwhile, your initial condition is inside. Where your initial condition is actually where my function is not continuous, there's no guarantee of existence of there is no guarantee that a solution exists. If you fail the existence of a solution, doesn't mean that you don't have a solution. It's just like your solution is not guaranteed. Then you need to really do some additional work to make sure that this thing is legal. For this case, of course, you can try it by yourself. You don't have a solution. Okay, it's simply not doable. You start from 0, you don't even know how to change. because at 0, your derivative is basically infinity. Okay? Everything else we had before, very quickly, you can see this, and you can see, okay, this one is going to be nice. Why? Because your y seems to be super good. Okay, no matter where you go, it's going to be continuous. So pick this one. Logistic, it's nice. Okay, pick the exponential growth. It's also nice. So for a lot of things in real life, from here you can see, okay, you will mostly see the nice cases for simple motions and simple growth. So that's nice. Mostly it's the solution exists. Okay. Now, second thing, we want to talk about uniqueness. And we have done some solutions before that the solution is actually not unique. So we do know this is necessary. Okay, so let's do it. For this one, we actually basically say the same thing. Suppose your right-hand side is nice, is continuous. All right. Meanwhile, you want your partial derivative of f with respect to y is nice, which means continuous. Okay. If these two are satisfied in an interval of x and y, t is between a and b, y is between c and d. Okay. Then, if t0, y0 is in this rectangular area, and you have two solutions, are two functions satisfying the initial value problem? Y0 equals y0 equals yt0 equals y0. Okay. Then we will have a conclusion. That is for, let's see, for then y1t equals y2t. Of course, only for this interval of t, where the solution exists. Okay. So what are we saying here is basically if you have two solutions that both solve the same problem, then these two solutions are the same, indicating you only have one solution. Because if you have two, it will be the same as the previous one. Okay? So from here you can see everything works as before. You want something here. You want the derivative to be nice in a fixed rectangle, and then you will have a guarantee of existence of solution within this rectangle. No problem. But this time, to make it unique, you will need a requirement, additional requirement, that is, this has to be continuous. Okay, that will guarantee this. Everything else is just for existence. Okay, so if you require a little bit more, you will have uniqueness. Well, is that so? Think about it. Let's try to take an example. Okay, let's take an example where we can have y prime equals 3y 2/3. Okay, y0 equals 0. Now check. You want a rectangle including 0, 0. And you can see clearly this one failed because partial, let's see, fty equals 3y 2/3. Okay, then partial y is going to be 3 times 2/3 times y to the negative 1/3. Not continuous at 0, 0. Therefore, the uniqueness fail. Then the conclusion is not that your solution is not unique, but your solution possibly can be not unique. Okay? What trouble does it give you? Well, let's solve it. One way you can do it is, this is separable, so you can do y to the negative 2/3 y prime. Now we do dt equals 3 dt, and then we can take the integration. All right, so this is dy, separable. So we have 1 to the 1/3, 3, okay, equals 3t plus a c. So finally, your y is going to be t plus a c over 3, which is just a 3, a c to the cube. Now plug in y0 equals 0, you can imply c equals 0. Therefore, the final solution is going to be y equals t cubed. You can plug in, this is certainly one solution. But now, by looking at it, can you find another solution right away? That is where we say, well, if you divide y on the other side, you ignore a possible case. What is it? That is, your y can be 0. So, plugging y equals 0, y is equal to 0 satisfies y0 equal to 0, and of course it satisfies the differential equation. So, we have two solutions, which is no surprising because you fail the uniqueness of solution. Of course, it's possible you have two solutions. So what's going on here? Well, that means starting from the same point, following the same changing rate, you will have one possible solution and you have a second possible solution. So if I ask you to predict the future at 20, at 4, which one are you going to take? It's going to be confusing, right? Second, now if we do the Euler's method, think about it. If you do the Euler's method for this, what's going to happen? Your Euler's method is going to track the direction field, right? You are going to track one and just keep going, keep going, keep going, keep going. You will only be able to track either this one or this one, but not both. Okay, we can do it. Euler's method. And you can easily see we can only track the solution which is not interesting. We cannot track the one with t cube. Okay. And regardless of how many points you take 10 points. Well, it's going to be that. You take a 10,000 points. It's still going to be the same thing. So from here, you can see your Euler's method cannot even track this solution, which is probably the solution we are interested in. And why is that? Very simple. Yk equals yk plus h. Okay. F, T, K, Yk. Now, regardless of what h you take, your y1 is going to be your y0 plus h times F, T, K, Yk, which is 3y 0 to the 2/3, but your y0 is 0, which will make the whole thing here 0. Therefore, your y1 will equals to y0 no matter which h you get. If your y0 is 0, your y1 is 0. If your y1 is 0, your y2 is going to be 0. So Euler's method will only be able to track this one. It will never be able to track this one. So if we have something a little bit more complicated, which you cannot write down the solution to be as easy as y equals t cubed, your numerical method will fail also. That's why we prefer not to have non-uniqueness. We want a unique solution, which is nice. So how do you do that? One possible thing is actually you change your initial, you start from 0, but I mean, does it hurt if you just start from 0.0001, which is basically barely a little bit bigger than 0, and suddenly you will have the other solution. And you can check it's y equals t to the cube. So by knowing the solution is not unique, you were able to figure out how to modify your Euler's method. You simply change your initial value from 0 to 0. Okay, something a little bit bigger than 0. Suddenly you avoided this kind of lock. The whole solution is to 0. You start to actually proceed in the blue line you want. Okay, so knowing uniqueness is going to help you to modify cases like this. And of course, the best case is actually we do have uniqueness. Then we don't have to worry about this. We can just go ahead and do numerical methods. Okay. Of course, this is not a very careful discussion because we kind of changed the initial value. Well, you may ask, like, what's the big deal? What's the big difference between 0 and 10 to the negative 7 or 10 to the negative 8 as I wrote down? It's not a big deal. Okay. But the problem is, whatever which is not a big deal at the beginning may become a big deal when you let it run for 10 million years. Okay, and if you care about what's going to happen at the end of the universe, you better be very, very precise of your initial values. So this will raise another question, that is the sensitivity. Of the solution with respect to the initial value. If it's not sensitive, then fine. Your initial value is 0, your initial value is even 0.1, may not change the final solution too much. So even though you don't get the exact solution, which you will never get because, how do you get the initial value? You get it by measurements. And your measurements naturally has some precision. You will never get the accurate initial value. It's only an approximation which with very high precisions, right? So if your solution, your ODE, is not the solution of the ODE is not very sensitive to the initial condition, then if you have a small error in the initial condition, won't be too much of a big deal. But there are systems that are very sensitive to the initial condition, which means if you slightly modify the initial condition like what we just did, the solution will be completely different. Okay, so before you actually do this one naively, you need to ask yourself, do we have a system that is very sensitive to the initial condition? For that, we refer to something called chaos system. That is some system that is very sensitive to the initial condition. A famous example is actually Punckley's three bodies problem. But it's not the only one. Probably the most famous one, the three-body problem proposed by Punckley. So if you're interested in this side topic, talking about the sensitivity of the solutions with respect to the initial value, especially if you want to factor in the precision of your measurement at the beginning, you better look this up. Okay, the keyword is chaos system, and Lorentz equation, three bodies problem are problems that falls into this category. That is going to be difficult to analyze. Okay. All right. So from here we can see, number one, we do have a uniqueness theorem, and it's fairly important. One more thing we want to talk a little bit about is the proof. I would say pseudo proof, not the exact careful proof of the uniqueness theorem. Basically, how can we see the connection between the partial derivative and how somehow this one was connected to y1 equals y2? Okay, why do we need this condition? We cannot give you a complete proof, but I think the idea is fairly simple. So what we know this? Well, we know y1 prime equals ft t y1. Okay, y1 0 equals y0, not 0, t0. Fine. Meanwhile, we know y2 also satisfies the same differential equation and the same initial condition. Okay. From here, we know two facts. Number one, we know y1 t0 equals y2 t0 equals the initial condition. Basically means y1 equals y2 only at t0. So what's going to happen is, if you have two solutions, at least they start together. It's possible that they, separate after a while, but at least they start together. Now second, what do you have? You take the first ODE minus the second ODE, you kind of have this. y1 prime, okay, equals ft y1 minus ft y2. Okay. Now, when y1 minus y2 is small, is very small, which you can have at least for a small period at the beginning. They should be relatively small. They are 0 at the beginning. So for a short period of time, they are going to be small. Then this one will be almost like something look like this. Okay, technically it's not equal, but when things are small, you can imagine. How do I say this? Let's just do this. The idea is similar like y, how to say, y2 minus y1 is almost like f prime y, y2 minus y1. Not this way. How do I say that? Let's say f y1 minus f y2 divided by y1 and y2 is almost like f prime y. Okay, given that y1 and y2 are close to each other. Okay, I ignore the t, so this is technically the definition of derivatives. Okay, when y1 minus y2 is small. We are familiar with that. Okay, but now I'm just applying the same analogy to partial derivatives. All right. So if this is continuous, that means this number is roughly, this number is roughly finite. Then this one is very likely a new function who satisfies a differential equation, that is y bar equals y1 minus y2, which is y bar, with a constant for a short period of time. Moreover, we know y bar equals 0 at t0, because at first y1 and y2 are the same. From here, you can see you have exponential growth with initial condition to be 0. Therefore, this will guarantee y bar equals 0 for a short period of time. Okay, so basically the idea is if this is 0, then it can guarantee that for a short period of time it's going to be 0. Then it may differentiate. But then you can replay this technique again. It will make sure that they are the same again. Then you can keep doing this. So following a careful mathematical construction of this is not too careful, you can actually construct the uniqueness for a longer period of time. For details, check something called Gromwell inequality. That is the major tool you need in order to prove this carefully. But for now, we kind of show you the idea that y partial f partial y is involved. You're trying to basically make sure that if y1 minus y2 is going to be small, then the change of y1 minus y2 is going to be small. Therefore, initially close will make sure that your difference won't grow too quickly. Therefore, initial no difference will give you no difference as time goes by. All right. So that's what we have for existence and uniqueness. Next time, if you see a new initial value problem, probably you want to run them through the uniqueness theorem first. If they pass, you can imagine the whole thing is going to be probably smooth, no matter you want to do numerical solutions or whatever analysis you want to do. If they fail, you need to take extra caution to make sure that what you are doing for the analysis are legal. And every time, you always need to think about multiple possibilities if the solution is not unique. All right, of course. We want to look at applications. It's very important applications, actually. Okay. Especially we want to talk about uniqueness. What do you mean? What's the implication of uniqueness? Well, the first one is very easy. That is, the future is uniquely predictable. That means what? That means basically the experiment is reproducible. That is very important in all our understanding of physics. For example, if you do free fall, okay, you take a ball, you just make it let it naturally fall from a tower. You do the experiment for once, okay? You do the experiment for the second time, setting exactly the same condition. You are expecting to get exactly the same results, right? If you just release the ball, half the time it goes down, half the time it goes up, half the time or maybe 1/3 of the time it goes down, 1/3 of the time it floats, and the third of the time actually this ball just keeps floating and never moving, then there's no way you can actually predict the future. There's no point of doing experiments because the outcome of experiment depends on nothing. Basically, if you set the same condition without additional parameters, there's no way you can actually fix which outcome of your experiment is going to be. That's going to be a disaster. So in real life, it's very, very important because you want every experiment to be reproducible. No matter you do it for 1,000,000 times, you still should get the same answer. Okay? Second, which is more interesting in a mathematical sense, that is the solution of the same ODE do not intersect each other. Let me explain what I mean by that. Okay? So remember, we were doing logistics. And we were trying to do the vector field. You have a lot of possible vector fields. So which solution do you have? Well, you may have a solution like that. You may also have a solution like that. And you may also have a solution like that. And many, many others ones. Depends on which initial condition you have. Okay, think about it. ODE only give you the vector field. It does not give you the final solution. So you still have multiple possibilities. Okay? Which one do you have really depends on your initial conditions. Fine. But then you start to ask a question. The black one is a solution. The red one is a solution. The green one is a solution. But do they intersect each other? In other words, will the black one and the green one, or will there be another solution that satisfies this? They intersect. Is that possible? Now with the uniqueness, you can easily tell it's not. Why? Because if you have something here, which belongs to the ODE, you have something here, which belongs to the ODE, you just draw a small box. And you take this one to be your initial value, and suddenly your solution is not unique. Then the solution is not unique. For what I just draw here with the initial condition here and the ODE. And the intersection as your initial value. Okay? It violates the Uniqueness Theorem. So if you already know that your solution is unique, then there is a guarantee that no matter how you draw those kind of solutions, they will never intersect. And that becomes very useful. Why? Well, think about this example again. This one has many, many solutions, right? We know 1 is kind of like the threshold. Okay, below 1, you go like that. Logistic growth, capacity. Above 1, you go like that. Okay. What about exactly 1? If you solve this one, what's going to happen? Well, then y prime at 0 is going to be y times 1 minus 1, which equals 0. That means starting from 1, you never change. That means this horizontal asymptote is actually itself a solution. It's a very special one. So if you're below the capacity, you grow. If you're above a capacity, you drop. But if you're exactly the capacity, you don't change at all. So not only they are the solution, this one is also a solution. And you can check this one is also a solution. If you start from 0, nothing change. Okay? Then the question becomes interesting. Can you grow? And eventually you grow like that. That means if you're below the capacity, can you somehow temporarily just boost your whole population above the capacity? Instead of actually approaching it gradually, you can actually go up and then go down, which still doesn't violate the capacity. You just temporarily violate it. Okay. Now, back to the principle. Because the capacity itself is already a solution. Okay? And your solution cannot intersect each other due to the uniqueness theorem for logistic growth. Therefore, this case will never happen. That means what happens below, stay below. What happens above, stay above. They never intersect. Then this solution here, which is the capacity, and this solution here, which is 0, kind of divided all the possible solutions into several non-intersecting areas. Then we can do them cases by cases. If you belong to area 1, this is what happened. If you belong to area 2, this is what happened. Those kind of solutions are very interesting. We call them equilibriums. Because they are the solutions that if you start from a value, you stay at the value. You never change. A solution that never changes, or that stays at the initial value. Those are equilibriums. It's very easy to find them because you just need to find where the derivative is 0. Because if the derivative is 0, that means you never change if you start from that value. Okay? And then they naturally divide the whole plane into multiple possible areas. So you can study them separately. That's nice. And why is it useful? We can already do it. Okay. More examples, of course, are coming for equilibriums in the coming sections. It's a very, very important concept. But even just for now, I can give you an example. Remember the one we did before? Where the Euler's method fails miserably. Okay. We can redo it again. We take that one, we take 10 points. Okay, it fails means, we don't even know it's failing or not because this looks, kind of okay. You do 20. Still maybe reasonable. Maybe 50. Now let's see the problem, and maybe even 100. You trust yourself less and less because this one starts to look a little bit ridiculous. Okay, then you start asking, like, what's going on? What's really going on here? Okay, am I doing the right thing? Is it because the numerical method failed, or is it because I coded something wrong, or is it because the original function actually looks like this? The solution will look like something nice and then start to bump back and forth. Which way is it? Okay, then you can do a very simple analysis. That is, I found equilibriums. Y prime equals a to the t sine t equals 0. Then you will find if you start from sine y. What did I write? Sine t, sine y. Okay. Sine y. Now, if you write down the solution, you can find sine y equals 0 will give you y equals 0 and y equals 2 pi and y equals 4 pi. That means if you write down your solutions, if you start from those kind of special values, you should stay unchanged because your derivative equals 0. So 2 pi, 4 pi. What happens below, stay below, otherwise you intersect. Once you intersect, you violate the uniqueness of solution. Similarly, the same thing here. Then, if you look at your solutions about what you just draw, okay, let me say it. So if you to look at the differential equations, we solve it. We have y equals 0, 2 pi, 4 pi. Those are equilibrium solutions. That means this is actually a solution. Everything I draw here. Okay. Now if you have some solution which looks like this, like the one we get from the numerical method, the moment you know that, you will know there is something wrong with your numerical method. Why? Because you intersect your solutions, and you are not supposed to intersect because you have a very nice derivative. Therefore, you should have uniqueness. Okay. Then automatically, now see what I draw here. The green lines are 2 pi and 4 pi. They intersect. Therefore, your numerical method is wrong. Okay. With that in mind, then you probably start to modify it a little bit. For example, you can give it more points. Now you see, well, when I bump everything up to 2000, which is way beyond the first time I imagined, I would say like 200 is pretty nice. It's a lot. But now if you bump everything to 1000, things start to behave at least the way you expected. Okay? It never cross any equilibriums. That means your solution never intersect. So you do not violate the uniqueness of solutions anymore. So this one looks more reasonable, even though there is still no guarantee this is correct. Okay? But at least I know this one is definitely going to be wrong. The one at the beginning. This is definitely wrong. So that's not the behavior of the solution. All right, that's everything we need for uniqueness and the existence of solutions.